It'd be nice to think about it. But see, structure in this has to exist. And you can tell that because we know how big these terms are, and we know that it has to be normally distributed. So there is a lot of structure in these polynomials. And you can tear out little nibbles of that structure, but we couldn't ever find any patterns and actually get enough structure to prove what we wanted to prove. So this plan failed.
They can only go up to probably take the Stam and find the first 10 moments.
No. We have like 23 or something.
Yeah, they can go up to 23.
Yeah.
And if you see they converge, they will go enough for me.
Well, the picture when it was 100 is enough for me. But yeah.
Sorry, maybe I should actually ask it.
Yeah.
But can you say anything about how you prove the existence of that formula? Or is it?
I mean, I can this formula.
Just an idea.
Yeah. In this example, you can almost. So the generating function, we couldn't write down like an explicit version of the generating function, but we could write down some some structure that it had, some properties that it had.
The recursive description of the generating function.
A what?
Some recursion for the generating function.
Yeah, kind of, but there's some weird differential operators in there and things, and so it's a little funny. But from that, we could prove this theorem. But I'm going to prove something much more general,
And you have
which wasn't
efficient algorithm
exactly like that.
Print out many of them up to big K.
Yeah, the algorithm is you use the first trick to compute the distribution. Once you have the distribution, you can explicitly evaluate this for n up to 100.
Oh, so you do it.
And then there's only so many degrees of freedom inside here, and you can solve for the coefficients.
So by undetermined coefficients.
Yep, that's right. That's what we do. Yep. Okay, but I want to talk. So we failed to prove this, but
If you go ahead, the paper was proved that the first 23 moments converge to those normal distribution.
yeah, and they do. And you can check it, and you can check the asymptotics of the terms. It's a little tricky, but you just get a computer to do it for you. Okay. Even then, it's a little tricky, but you can do it. Okay, so with these formulas, these things look pretty interesting. Okay, so these formulas are all over the place. So, for example, if you look at the crossing numbers. So if you aggregate the crossing numbers over all set partitions of n, there's a formula like this. It's minus 5 b of n plus 2 1 b of n. If you look at things like the number of blocks in the set partitions of n, there's a formula like this. If you look at number of blocks of size I, so you fix I, and then you look at the number of blocks, this is n choose I. So this is just a polynomial, because I is fixed. This is polynomial in n, and b of n minus I. And if you look at, there's just any statistic except a handful of things. A lot of statistics have these shifted Bell polynomials as their aggregates. And so this sort of game, you should be able to play it, just for anything you want. And that's the real theorem that we were led to from this investigation. Okay, is that if you have a statistic on set partitions, then that statistic in its aggregate is a shifted Bell polynomial. So I'm going to define what I mean by statistic, and it takes a little bit of setting up to tell you what I really mean, and then I'll tell you kind of more detail about the theorem. The theorem is basically this theorem, but it's true for all statistics. Okay, so loosely, a sort of loose definition is that a statistic is counts the number of occurrences of a pattern. Okay. So, for example, if you want to count crossings, that's a kind of pattern inside of the arc diagram that you just want to count all the times I see that pattern. Okay, so here's definition. So a pattern of length k is defined by a set partition of k. I'm trying to debate actually, because I worry I won't have much time to tell you about Stam's algorithm, so maybe I can abbreviate this part, because it's just kind of technical.
But the D statistic
Okay,
is
so-
also,
Say again?
the D of lambda is a...
The D of lambda will be a statistic, the crossing numbers is a
You know,
statistic.
obviously, well, what the patterns?
Okay, I'll give the definition.
Yeah.
I'll give the definition. Okay, so a pattern, and I'll sort of abuse notation. A pattern P of length k is a set partition, so I'll of k, right? And a set which I call F, which you can think of it as first. So you're going to say this thing has to be in the first element in a block. L of P is like last. Those are both subsets of the set K. A of P, which really means arcs, and C of P, which means consecutives. So things that, so you're allowed to like decorate elements by saying this is going to have to be next to some other element, or this is going to have to be, you know, there's going to have to be an arc between them. Consecutive meaning the difference is 1, right? So you can generalize even this definition in some ways. So this is going to be pairs, sort of ij, or I less than j, right, contained in there. And then, so that's a pattern. So an occurrence of a pattern P in lambda is, well, it's a tuple, a k tuple, right? So here, x1 is less than x2 is less than xk. Okay, where we have the following properties. So xi should be in the same, this means in the same block as xj, if and only if I is in the same block as j in the pattern P. You also want xi should be in a first of lambda if I is in this decorated set. Similarly for L and lasts, has to be in the lasts. And you know, like xi and xj are arcs. This just means the things where there is an arc connecting them. If you said that it was I and j were going to have to be an arc between them, and this consecutives is xj minus xi equals 1 if, you know, if I and j are in this special set C of P. Okay, and when this occurrence appears in lambda, we write, where should I go? I'll go over here. Hey, can I erase this one now? Oh, it's so difficult. Okay.
If you want to get to standard, you don't have to give all the details about this. That's the big picture.
Right. Well, so now I basically said it. So I'll just finish.
So you have a formal definition.
Yeah, there's a formal definition. So to say that S is an occurrence of this pattern in lambda, we'll write it that way. Okay. So now a simple statistic is defined by a pattern and a polynomial Q, say, where, you know, what I want to be able to do is, like the dimension exponent, I cared what values of the thing were. I needed to be able to evaluate at the biggest thing and at the smallest thing. So it's f of pq of lambda is the sum over all of the occurrences of that pattern in lambda, and you can evaluate the polynomial at the values of that occurrence.
So it's a very general class of statistics.
Yeah, it's a very general class, right? And so the first theorem is that, well, and then this is a simple statistic, and then a statistic is any linear combination of them. And the first theorem is that it's closed under multiplication, so it forms an algebra. Right? Statistics form an algebra. Okay. So that means that if the dimension exponent is a statistic, then any power of it is as well. So if you want to compute any of the moments, you can do it. Right? Okay. And then the second theorem is that formulas always exist. Okay. And you can bound with bounds on the degree.
Of the same form with the shifted bell number.
Yep. Degree and range of summation. Right. So, in other words, you know how many degrees of freedom there are, and so you know how much work it takes to compute the formula. But it's an automated thing. Okay. For any statistic.
You have an algorithm.
What's that?
You have an algorithm to compute that.
Yeah. Right. Okay, so I only have 6 more minutes. And in that 6 minutes, okay, so that, we failed to prove normality, which is what Percy wanted, but I think we got a lot of interesting sort of computational things out of just playing around with these statistics.
So for the original idea of lambda, did you prove normality?
We did, and I'll tell you how.
Different approach.
Which is, we took a totally different approach, which comes from using Stam's. Okay. Right. So we failed to prove normality through sort of computing moments. Maybe you can do it by thinking about these polynomials the right way. You can find all these polynomials on my webpage as well, all the ones we computed. Okay, so Stam's algorithm, what it is an algorithm to generate a random set partition. Okay, so you fix a size and it generates a random set partition. The starting point for it is, I'm not sure whose identity this is. Rhoades, or maybe Levinsky. I don't know. Not sure who. Maybe both. Right. But here's the identity: is that the nth Bell number is 1 over e times the sum from n equals 1 to infinity of m to the n over m factorial. Okay, let's do an example. B of 1 is 1 over e sum m equals 1 to infinity m over m factorial. And sure enough, that's e. E times 1 over e is 1. Yeah, there's 1. Good. I like that. All right, so this gives, you divide by the b of n, you get a probability distribution. Okay, so 1 is equal to the sum from m equals 1 to infinity of 1 over e times b of n, m to the n over m factorial. Okay, so here's the algorithm. First thing you do is you pick, so n is fixed, you pick m according, with probability, probability 1 over e b of n m to the n over m factorial. And the second thing you do is you drop n balls into m bins. Label the balls 1, 2, 3, up to n. That partitions those n objects into some number of sets, into some number of blocks rather, but at most m blocks because there's the most m bin. That is a uniform. That will generate a set partition uniformly at random from the space of all set partitions. So now, if you want to understand things like the dimension exponent, what you do is you first fix m, which m is basically, okay, so here's a fact. The number of empty, so Stam proved this, the number of empty bins is Poisson, Poisson distributed with, with variable 1, with parameter 1. So basically, if you have your m balls, your m bins, you're going to miss one of them with your n balls. Okay, so what you do now, if you want to prove anything, I don't know, okay, you can prove a lot this way, is you first fix m. M is basically going to be the number of blocks in your partition. That's a classic problem. We understand how the number of blocks is distributed. Okay. But now you're dropping, to figure out what values are actually inside of your blocks, you're just dropping balls and bins. That's a problem we understand too. So you combine those two approaches together, and you learn what you want to learn. Okay, so that's how we proved. Okay, that's how we ended up proving the asymptotic normality for the dimension exponent. So I really like this Stam's algorithm, and I don't think it's as well known as it should be. That's really pretty. Okay, so I think if I can tell you more about this and give you a sense for how the proof actually goes, but I think I'll just finish by, I think I'll just close up with a couple words. So I wanted to tell you about 4 things, I think, today. So one was the Stam's algorithm, which I only got to sort of touch on. The second, but I think it's a really nice algorithm. The second was the existence of these formulas. So, these things are just all over the place, and I think they're really pretty, and that, there's reason they're all over the place. It's because they have to be, I guess. And the third thing was this marked set partition trick, which I thought was really handy in trying to recurse and compute these distributions. And then the fourth thing is just how much fun I think it was to work with all these people that all kind of have different backgrounds. Like Bobby is an electrical engineer versus a statistician, and Dan Kane is really problem solver. He's really good. So okay, anyway, it was a lot of fun working on all these things. Yep.
Thank you for a beautiful talk. Ron, be glad to answer questions.